It's not in the manual, yeah. It's a handout. All right, yesterday we left off where? What were we talking about?
Give us an example of the grams of iron.
Okay.
Potential energy.
Oh, potential energy. All right, so we're talking about the system then. So we're dealing with typically what we deal with is a closed system, right? And for most of it, we deal with a closed system that's at constant pressure or constant volume. Well, constant pressure, actually. At constant pressure, then, well, any system, whether it's at constant pressure or constant volume, we're going to have two types of those. And we have a system that can be an object, like the chunk of iron. Did I finish this? The change for a chunk of iron is just a change in kinetic energy. The other type of system that we're going to run into is a reaction or a process. And so for a reaction or process, it would be something like methane, the combustion of methane. And so the combustion of methane is our system. It's going to go to CO2 gas plus H2O liquid. But when we have a combustion of methane, what we want to do is we don't want the kinetic energy to change. And so we set the temperature. So it's 298 Kelvin at the start, it's 298 Kelvin at the finish. So even if the temperature changes during the course of the reaction, we just wait until the temperature goes back to 298. And so now what we say is that methane and oxygen has a higher chemical potential energy than CO2 and water. And so this is a much more reactive mixture than a mixture of CO2 and water, which isn't very reactive at all. And so there's going to be a change, and this change in energy, delta U, is going to be the change in potential energy plus the change in the kinetic energy. Well, here it's because we wait for the temperature to come back that we'll say the change in kinetic energy is zero. If there was a change in the kinetic energy, then we would have to know the specific heats of all these things and calculate the MC delta T for that, which is a hassle. We don't want to do that. And so here we're just looking at the change in potential energy. Did I talk about delta S of the universe? The second law of thermodynamics? Talked about the second law of thermodynamics. Okay. Did we derive the equation for the second law of thermodynamics yet? No? All right, so let's take a look at delta S of the universe. What's observed is in nature, what we want to do is we want to minimize energy and maximize entropy. And so what exactly is the balance? So we looked at it, I think we looked at it using dimensional analysis. Did we do that? So if we get the change in energy in units of kilojoules and per mole, and the change in entropy in units of kilojoules per mole, then we can compare them, right? The energy we want negative, we want it to be exothermic. Did I already write this on the board? Yeah? No? That is, we're looking at delta H versus delta S. Sometimes they work together, But when they work together, it's like delta H is exothermic, so energy goes down, entropy goes up. Minimize energy, maximize entropy, this is good. So here we have good and good. That's good. Sometimes they work together but oppose the reaction. So this is bad for driving force. This is bad for driving force, and we're going to get bad overall. So bad plus bad equals bad. But sometimes they oppose each other. So one might be good, the other might be bad, then what happens? Now we have a conflict, right? We have enthalpy says one thing, or energy says one thing, entropy says the other. And so how do we compare these? Or, you know, energy might be bad, and entropy might be good. And so what is that going to equal? That's the question. And so one of the ways we might try to look at this is by the dimensions. You know, because delta H, what are the dimensions of delta H? Delta H is in kilojoules per mole typically. S is in dimensions of joules per mole Kelvin. And so if we do this dimensionally, then we got to get rid of Kelvin. How can we get rid of Kelvin? Well, one way to get rid of Kelvin is just multiply this by the temperature in Kelvin. If we multiply this by temperature in Kelvin, then we can compare it, right? And so that's one of the things that we can look at. We compare delta H versus delta S. And then to get them dimensionally the same, we multiply T times delta S, and that will give us that. And then we convert it to kilojoules. When we convert it to kilojoules, then we can compare kilojoules versus kilojoules. If we have kilojoules versus kilojoules, maybe it's a more fair comparison, right? But that's one approach. A lot of equations in physics have been derived using dimensional analysis, just looking at the units. The other alternative is something like this. The other alternative is from lots of observations. From lots of observations, the second law of thermodynamics was derived. So what is the second law of thermodynamics? The second law of thermodynamics says that for a spontaneous process, delta S of the universe must be greater than 0. That is, the entropy of the universe must increase for a spontaneous process. If delta S of the universe goes down, then it's a non-spontaneous. There's no driving force for that particular process to occur. The problem is how do we determine delta S of the universe? We can't consult Appendix D, right? Is Appendix D big enough to encompass everything in the universe? No. Obviously, it'd be too much work. And so how do we figure out what delta S of the universe is? Did I talk about this? We started it, but okay. Well, obviously, this is impossible, right? But this is part of the challenge of thermodynamics. Part of the challenge of thermodynamics is knowing the relationships of thermodynamics. You know, knowing them to the extent that you can apply them to different things. So you might learn one thing and apply it to something else. And so we do that a lot in thermodynamics. So it's not, thermodynamics is tough because it's not just learning it, but making all the connections, you know, the neural connections. Making all those neural connections does take time because all these relationships, all these equations and stuff. But anyway, one of the first things we know that the universe can be broken down into two parts. The universe can be broken down into the system and the surroundings. Well, that makes it a little easier. Delta S of the system is easy because this is Appendix D. You know, our system's either going to be an object, right? Well, it's an object we don't really use. Do we use Appendix D? Yeah, I guess we would. Or a reaction or process. We use Appendix D, etc. There are other data tables for this. But what do we do with this? You know, we run into the exact same problem because the surroundings is the rest of the universe. Well, this is the same problem we had earlier. The surroundings is the rest of the universe. But there's some thermodynamic relationships that we can take advantage of. One thing is that, okay, well, let's leave delta S of the system because we can deal with that. But delta S of the surroundings, well, what are some of the other ways that delta S can be determined? Well, there are other ways, S final minus S initial. Well, we aren't going to do that for the whole universe. But there's one that's Q reversible over T, you know? And so this is going to be Q reversible of the surroundings over the temperature. Now, what is Q? Q is heat. Right. Problem with heat is what we call a path-dependent function. A path-dependent function, you know, doesn't always give you the same amount of heat. So, for example, if you burn a mole of methane, you don't always get the same amount of heat because it depends on how you burn it. Especially if you do work. You know, if you burn a mole of methane in a natural gas vehicle, you know, CNG, compressed natural gas vehicle, you're going to do a lot of work, and hopefully you don't generate too much heat. Whereas if you burn a mole of methane on your stovetop, you don't want to do a lot of work. You just want to generate a lot of heat. And so the amount of heat varies because, you know, a CNG is not meant to be a stove and you're not meant to cook anything on it. CNG vehicle. And so the problem with heat is it's not a state function. But that's all right, at least because we know the first law of thermodynamics. You know, I told you one way. Did I tell you one way we express the first law of thermodynamics? One way we express the first law of thermodynamics is that delta U is equal to Q plus W. Heard that? What's another way we can express the first law of thermodynamics? Okay. What's another way? MC delta T, yeah. Okay, the energy change of the universe is 0. The total energy of the universe is constant. And yet there's another way. Another way of stating the first law is like this. From the first law, we can say that Q of the surroundings is equal to minus Q of the system. So whatever heat is gained or lost by the surroundings must have gone into the system or came from the system. And so the negative doesn't mean it's less than 0. The negative just means opposite in sign. And so if we could plug that in here because delta S of the system plus now a minus Q reversible of the system divided by T. Now this seems more reasonable. This seems more reasonable because we can measure the amount of heat gained or lost by the system just using a calorimeter. It's easy. Versus if we wanted to measure the amount of heat gained or lost by the surroundings, we'd have to put the rest of the universe into a calorimeter, which is not possible. But we still run into the same problem. You know, the amount of heat varies. And you know, if I burn a mole of methane, I want to know how much heat I'm going to get. And I don't want somebody to say, well, the amount of heat you get will depend. Well, that's true, but just tell me how much heat I'm going to get. Well, what we're going to do is this. You're going to say, well, the amount of heat you're going to get is if you always do it like this. You know, you set the pressure to 1 bar or 1 atmosphere, and you only do P delta V work. And so what we're going to do is we're going to do this. Heat can be made into a state function by placing 2 restrictions. So heat can be made a state function. The state function is always the same. It just depends on the final state and the initial state, not how you burn it. And so heat can be made a state function if, 1, we carry the reaction out at constant pressure, and 2, only P delta V work is done, the natural work. Well, in order to maintain constant pressure, if a gas is generated, the system's got to expand. If a gas is consumed, the system's got to contract. And so in order to maintain constant pressure, the volume has to be changeable. And that's going to require work. And so when we do that, then Q is defined as delta H. Delta H is we're always going to get the same amount of heat because we're always doing the reaction the same way, constant pressure and P delta V work only. And so what this simplifies into is delta S of the system minus delta H of the system divided by T. Oh, now this is getting better because delta H, you know, how many different ways are there to calculate delta H of the system? A lot. And so delta H of the system is an easy calculation to do that. And so we're going to do a little bit of simplifying here. T delta S of the universe is equal to, let's do it this way, delta S of the system minus delta H of the system. And so this has to be greater than 0 for the entropy of the universe to increase. And so in other words, we can calculate this using Appendix D data, or if we're given data, we'll just use that. Now we can calculate this using Appendix D data as well. And so both of those are easy to calculate for a system. We're going to multiply by -1, so we're going to get negative T delta S of the universe is equal to, and then reverse the positions. It'll be equal to delta H of the system minus delta S of the system. Actually, since I'm multiplying by T, minus T delta S of the system. Okay, since I multiply by -1, I have to flip this. So this has to be less than 0. If that's less than 0, then the entropy of the universe is going up. Temperature is always positive. It's the absolute temperature. All right, this term here is going to be defined as a new state function called delta G. G is the Gibbs free energy. Delta G is just equal to delta H of the system minus T delta S of the system. And we want it to be less than 0 for spontaneous reaction. So this is another way of representing the second law of thermodynamics in terms of the system here rather than in terms of the universe. And so let's take a look at the different scenarios that we're going to have. Delta G is equal to delta H minus T delta S. So if delta H is negative, that's good because the energy is going down. It's minimizing energy. Now if delta S is positive, that's good because the entropy is going up. And so if delta H is negative, that's negative. And delta S is positive. If positive times a negative is a negative, this whole thing is going to be a negative. And so this whole thing is going to be less than 0. And if it's less than 0, we say it's spontaneous. Now, if we have the opposite, if we go up, this is bad. And if we go down, that's bad too. Because that means delta H is positive, and a negative times a negative is positive. This is always going to be greater than 0. And so this is always going to be non-spontaneous. Now, what happens if there's a conflict? Well, this gives us a way of weighing it to see which term is dominant. And so let's say the energy is good because the energy is going down, and so this is good. However, the entropy is going down as well, and that's not good for driving force. And so this is going to result in two things. One, if energy is dominant, then we have reaction. If entropy is dominant, then we have no reaction. And so in order to make the energy term dominant, we keep the temperature small. And so we say that this is spontaneous at low temperature. At low temperature, temperature is small, therefore that keeps the entropy, the bad term, small. However, at higher temperatures, then the entropy term will dominate, and so this will be non-spontaneous at high temp. Let's say the energy is going up. That's not good. If the energy is going up, that's bad. However, the entropy is going up, well, that's good. If the entropy goes up, you want that. And so, well, entropy is dominant at high temperatures. This term will be dominant. At low temperatures, enthalpy is dominant. And so here, this will be spontaneous at high temperature. But non-spontaneous at low temperatures. Well, what is high temperature? What is low temperature? Well, it depends on the reaction. You know, that temperature that cuts it off is going to vary. But anyway, we have a way of comparing the energy and the enthalpy term. And when you look at it, this is kind of like what we got with dimensional analysis. We're just comparing, you know, these have to be in the same units, kilojoules and kilojoules. But we can see which one's dominant by doing the subtraction of the two. Now, is this really the second law? Because what was the second law of thermo? The second law of thermo was that the entropy of the universe has to increase. But did the second law say anything about the energy? Did the second law say the energy has to decrease? The energy of the system? No. And so where does the energy pop in there? And now, why does the energy pop in there? Because the second law was observed for the entropy of the universe here. And the energy pops in there because we have two types of entropy. We have entropy that's positional, you know, disorder. Is everything neatly ordered? Or are things disordered? That's positional entropy, you know, where it is in space. And so here, you have different positions for the test tube. And then we have another type of entropy. And so when we're doing our delta S calculation from Appendix D, that's positional entropy. You know, solids are neatly ordered versus liquids. Liquids are more disordered. Gases are even more disordered. That's positional entropy. The other type of entropy is called energy entropy. Energy entropy is this. You know, let's say I have 270 kilojoules worth of heat. Right. Versus, you know, the 270 kilojoules of heat would be something like this. You take a hot object, and you let that hot object cool down, so we get a cold object. And in the process, you know, we're going to, because this is just kinetic energy, it's going to give off heat. And we'll say 275 kilojoules. Heat. So let's say I want to power my my car with a hot chunk of iron. Is it possible? Because take a hot, well, that hot chunk of iron has, you know, high kinetic energy. So maybe I'll capture some of that energy by cooling that chunk of iron down. So, well, you can try to think of ways to make that. Well, you have, you know, what you can do is maybe take that hot chunk of iron, put it in water, boil the water into steam, and drive some kind of steam engine. And so maybe I could use this heat to drive a steam engine. Yeah. versus, let's say I have some gasoline and O2. Gasoline and O2 has high chemical potential energy because, you know, eventually when you combust that, you're going to get some CO2 and water and some other stuff, etc. And so let's say I have 275 kilojoules worth of energy stored here. And you say, well, this is 275 kilojoules, this is 275 kilojoules. So what would you rather have? Would you rather have me give you a hot chunk of iron to power your car, or would you rather have me give you some gasoline? Probably some gasoline, right? But you know, it's 275 kilojoules is 275 kilojoules, isn't it? No, it isn't. It isn't, because this 275 kilojoules is just heat. That heat is what we say a more disordered form of energy, right? So this 275 kilojoules is a more disordered or higher entropy form of energy. Whereas this 275 kilojoules is wrapped up in potential energy. And so this 275 kilojoules is a more ordered form of energy. And with a more ordered form of energy, then we can more easily convert that into work. So for example, I could use this to generate electricity quite easily. You know, just buy a generator, gas generator, and then run it. Could I use this to generate electricity easily? No. I could use this to do mechanical work, you know, drive a car. Can I use this to do mechanical work easily? No. And so these are different, you know, even though it seems the same because they both are 275 kilojoules, but they are different in terms of the quality of the energy. And so, and the way it differs is this is a higher entropy. Once you're at a high entropy, you know, you have much driving force left available. This is going to be at a lower entropy. And so this is it. When we dump heat into the surroundings, you know, we could have, you know, when we dump heat into the surroundings, that heat is a high entropy form of energy. Both of these are going to end up, even if we do mechanical work over here, and even if we generate electricity, eventually all that energy is going to end up as heat, you know, in the surroundings. And so, basically, if a reaction's exothermic, then we must be going to from a, what should we say, a lower entropy energy to a higher entropy. And so exothermic reactions are you're going from lower entropy energy to higher entropy energy, and therefore the delta S of the universe is increasing. All right. That's it for this that I wanted to talk about. Just finish up this a little bit here. And then let's talk about the lab. Unfortunately, I thought the Spartan was working, but when we went into the lab this morning, Spartan was not working. What is Spartan? Spartan is the quantum mechanics software that I was hoping to use for acid strength lab. So with Spartan, what Spartan does is it does the quantum mechanical calculations for you. The Schrodinger equation stuff, all that. And so what was quantum mechanics all about then? That chapter 8, I think it was. Quantum mechanics is all about what? The electron. What do we know from quantum mechanics about the electron? Well, in quantum mechanics, what we want to know the energy of the electron. You know, we have all these energy, you know all the energy level diagrams? This is another energy level diagram, but these are energy level diagrams for thermodynamics. From chapter 8, we had energy level diagrams for the electron. And so, you know, we have some kind of energy axis going up like this. So we want to know the electron energies, you know, from quantum mechanics. But there's something called the Heisenberg uncertainty principle. What was the Heisenberg uncertainty principle all about? Yeah. All right. Speed is energy. And so, one, you can't know both with certainty, right? You can know both, but the level of uncertainty is going to be high in both. And so what we can do is we can make a compromise. For example, we can know the energy and pinpoint the energy, but if we pinpoint the energy, what does that tell us about the position? Well, that tells us there's going to be some uncertainty in the position. Or we can pinpoint the position, but that means we don't know the energy so well. And so in chapter 8, what did we do? Did we pinpoint the energy, or did we pinpoint the position of the electron? We pinpointed the energy of the electron. If we pinpoint the energy, then the position is not totally uncertain. That, you know, the uncertainty in the position is not infinity. But the uncertainty in the position is given by an orbital, right? An orbital has a boundary, you know. So, for example, you know, when we look at an orbital here, there's some kind of boundary, and that boundary is a probability boundary. And so that means, you know, the position of the electron might be here, or might be here, or might be here. And so within this boundary, there's a certain percentage of finding that electron versus outside the boundary. Outside the boundary, there's going to be a lower percentage. This boundary is not a wall, it's not a fence. It's just a statistical boundary here. Do you remember what the percentage was? We would say that there is a 80% chance of finding an electron within this boundary? Or was it 90%? Was it 95%? What was that percentage? 90? Does anybody remember? Yeah, it was probably pretty high, so it's just a high probability. That's what we can say. The actual number isn't so important. In this case, we don't really have to know. I mean, if it's 90, 95, whatever. But it will tell us, you know, the relative size of the distribution here. And so there's a high probability of finding it. Now, as we get to higher and higher energies, that size grows bigger. The orbital. These are called orbitals, right? And orbitals are have electron dot diagrams, we call these, or we call these electron clouds. That type of stuff. What Spartan does is it looks at how the electron cloud is distributed in the molecule, because chemistry deals with electrical interactions. Electrical interactions. And so let's take a look at acids in general. So this lab we're going to do is we're going to take a look at acid strength based on structure. And we're going to use Spartan to determine the structures of these, including, you know, how the electron cloud's distributed in the molecule. And so let's look at the factors that affect acid strength. Okay, the most important factor that affects acid strength will be the HX bond strength. And so, for example, HI versus HBr versus HCl versus HF. HI has the weakest bond. Since this is the weakest bond, well, we can see that in quantum mechanics as well. Because if we look at iodine, you know, and we can visualize it in different ways, but iodine could have an sp3 or p orbital. Depends if you want to hybridize it or don't. For large atoms like this, we don't necessarily have to hybridize, because one of the purposes of hybridizing is to minimize the repulsions. But if it's a big orbital, then the repulsions aren't going to be significant. And then this is going to bond to the hydrogen here. This is more of a valence bond picture, but basically what we have is you have electron density. And the positional probability is going to be given by this cloud here, the electron dot diagram. And so that's the weakest bond. The strongest of these would be HF. So if we have fluorine here, you're going to have to hybridize this. You know, fluorine's kind of small. So the other orbitals, the three other sp3 orbitals, are going to really repel here. And the H here. So what makes a covalent bond? You know, what holds the hydrogen and X together, like in this case iodine and in that case fluorine? You know, a covalent bond is held together by what? A lot of people will say overlap of orbitals. And so if people say the atoms are held together by the overlap of orbitals, right? Does that mean, you know, the boundaries here kind of latch onto each other? Is that it? No, because the boundaries are, these are just, there's no real boundary there. It's just some kind of statistical line or limit. Maybe they're held together by sharing electrons. So the overlap there doesn't really, but sharing, you know, if they share nicely, you know, then is that a stronger bond than if they don't share nicely? I mean, sharing electrons, how do they hold the atoms together? You know, is the sharing, I mean, how exactly is sharing electrons holding the atoms together? So HF shares electrons nicely, and HI doesn't share them as nicely. And therefore, HI is a weaker bond because it's not sharing fairly. And HF is a stronger bond because it shares very nicely. Does that make sense? Is that a good argument for why the HF bond is much stronger? Not really. I wouldn't say overlapping because, I mean, it's true. Actually, both, you know, it's not wrong. Both are true, but it really doesn't get to the gist of why the atoms are held together. Why are the atoms held together? There are no pi bonds. This is just sigma bond here. You know, sigma bond is along the internuclear axis.
Because of the size, like the electron affinity for fluorine, because the size is smaller.
It has to do with size too, yeah.
So if there's like smaller, when the orbital is smaller, then the electrons are shared like more closely and compactly. But if when they
Yeah. Well, basically, you know, all those factors are right. All of those factors influence it, but what really holds these atoms together is the electrical attraction. Is the electrical attraction between the nucleus and the electron cloud. The electron cloud is negatively charged. And so over here, the two nuclei are going to be attracted to the electron cloud. Where's the electron cloud concentrated? Well, the electron cloud is concentrated between the two nuclei here. And so we can see there's going to be a strong bond. Over here, the two nuclei are going to be attracted to the electron cloud, but the electron cloud is more spread out. You know, the negative charge density is concentrated here. And so all this has to do with overlap. All this has to do with size. All this has to do with sharing. But ultimately, what holds the two atoms together is the attraction of the positive charge in the nucleus with a negative charge in the electron cloud distribution. And so this is why quantum mechanics is so powerful, because quantum mechanics can tell us how the negative charge or the electron density is distributed in the molecule. And from that, we're going to understand things like bonds. We're going to understand things like intermolecular forces. We're going to understand things like acid strength as well. There's a diagram in chapter 9. You know, this is arbitrary zero in energy, and this is bond energy. So, you know, what is the zero for bond energy? Well, there's no absolute zero. This is going to be relative zero. So what we have are two hydrogen atoms spread apart infinitely far from each other. And then as we bring the two hydrogens together, then the energy drops. And so here, this is the optimum bond distance. The optimum bond distance is where we balanced out the repulsions and the attractions. So there's going to be attractions. When we have overlapping orbitals, what the overlapping orbitals does is it concentrates more electron density there, because each one is a 90% boundary here. And so we're going to have more electron density concentrated in the internuclear region, in the region of overlap. And that means there's more negative charge there, which holds the nuclei together. And so what we do is we'll take them from infinitely far apart and bring the atoms together. As we form a bond, the energy drops. If we try to push the atoms too close to each other, then the nuclei start to repel each other with more force. So here we try to squeeze them too close together, way too close together. The nuclei get way too close to each other, and they begin to repel each other. And so there's going to be an optimum bond distance. All right, so when we form a bond, energy is released. And so if we just say zero is, you know, where there's no bond, then this would be the bond energy. When we break a bond, energy is consumed and break it. And so bond formation, bond breakage. Well, the hydrogen-hydrogen bond is like 400 plus kilojoules per mole. And so this bond is quite weak. Look at the electron cloud here. This bond is quite strong. But it turns out when we're looking at the acid strength, HI is stronger. HBr is stronger than HCl. And HCl is stronger than HF. But it turns out HCl is a heck of a lot stronger than HF. And so what it is HF is unusually weak. Why is HF unusually weak? Well, one reason is HF is unusually weak because it's 1,000,000 times less acidic, 1,000,000 times weaker acid. 1,000,000 times weaker than HCl. And so it's unusually weak. Well, maybe HF has a million times stronger bond, right? And so the bond energy for HCl, the bond energy is 300 to 400 kilojoules per mole. And so let's just say around 300 kilojoules per mole. That's the bond energy for HCl. You know, how much energy we would have to input to break that bond. Does that mean the bond energy for HF? Oh, the bond energy for HF must be 300 million kilojoules per mole. Let's do kilojoules per mole here. 300 million kilojoules. Does that sound like a reasonable bond energy to you? 300 million kilojoules? What's the strongest bond you know that you've heard of so far? A billion kilojoules per mole? Somebody said, yeah, I got a bond energy, it's a billion kilojoules per mole. What do you say? No. Even 300 million? If somebody said the bond energy is 300 million kilojoules per mole, what do you say? You'd say that's crazy. Crazy amount of energy. There's no way. 300 million kilojoules. And if it was true, then maybe you hit on something. You hit on something that's stronger and less reactive than anything. Because, you know, the strongest covalent bond on the chart, is the nitrogen-nitrogen triple bond at 1,000 kilojoules per mole. And so do you really think HF, in fact, HF bond is on that chart. Is the HF bond a million times stronger? No, it isn't. And so HF is outside the trend here. And so why is HF outside the trend? It doesn't have to do with the bond energy. Usually weak, a million times weaker than HCl. This cannot be the bond energy for this. HF is unusually weak because of ion pairing. What happens is if we have HFAQ and we try to break apart, you know, to get an H plus and an F minus, the problem is that F minus is very small. That means it's very small and it has that negative charge, means it has a fairly high charge density. And so we got concentrated negative charge from the small volume, which means that, you know, electrically there's an attraction here. And so initially when we break it apart, it doesn't completely break apart. If it doesn't completely break apart, then this is not a free proton, i.e. a proton that's able to react with bases. This proton is kind of stuck with the fluoride here, which is going to bring its reactivity way down. And so in order to free up the proton, to get a free proton, it's going to take another hit, another collision, and then we'll completely break the two apart. And so because of this ion pair formation here, that dramatically weakens the strength of HF. Whereas HCl doesn't have this problem because chloride is a much bigger ion. And so it's going to be less reactive in the sense that, you know, fluoride has negative charge concentrated here, but chloride's negative charge is spread out more. And so the H plus isn't going to be as strongly attracted to it as it would for fluoride. And so chloride does not have this problem. This problem. All right, so bond energy is the number one factor. The number two factor is bond polarity. And so let's talk about bond polarity. Let's take a break for 10 minutes or so, and then we'll talk